Okay, so potential energy. There's two different types of potential energy. One that we're going to talk right now is about gravitational. So potential energy is basically stored energy in an object. So when there is a certain height above the ground, it has a certain amount of stored potential energy. It has the potential to do work. If we think about it, if we hold an object above the ground, so let's say, here I am, I've just lifted a box up above the ground. So I'm going to lift it up, I'm going to have an applied force upward, and I'm going to lift it this certain distance, a certain height. Okay? We're going to call this, height is also equal to distance, since they're both variables for distance. Okay, it has the potential to do work. So let's make sure you write that down. For example, it has a certain amount of energy when I lift it from the ground to a certain height. If I were to drop it, what's the box going to do? Well, the box is going to fall towards the earth, towards the center of the earth. So it has the potential to do work. Okay, the units for potential energy are joules. So let's go ahead and derive the equation of potential energy. Okay, so in life we need to know that energy is always conserved. So the energy that something has initially is going to be the energy it has at the end. It just may not be in the same exact form it was originally in. So we can say that energy initial equals energy final. And right now I've done work on the box, so it has a certain amount of joules. So work is going to be converted into potential energy. And specifically potential energy gravitational. So we're going to use the G for gravitational. We're going to discuss another potential energy in the next video. So work, well, we know the equation of work. Work is equal to force times distance. So right now I'm going to show you how we derive potential energy gravitational. Well, we also know that this force that it required to lift it up, it was the force of its weight. So the weight of this box is equal to mass times gravity. So this force is equivalent to mg times distance equals potential energy gravitational. And once again, another convention in physics, we always call, when we talk about potential energy gravitational, our height is referred to as an h, not a distance d. So let's replace this d with an h. mgh equals potential energy gravitational. So that leads us to our equation. There it is. Pe subscript g for gravitational is equal to mgh. And the units for everything, well, you know, mass is kilograms, h, height, is meters, g is 9.81 meters per second squared, which leaves us with potential energy is in joules. So let's do two examples. For the first example, I want to know how much does the gravitational potential energy of a 64 kilogram pole vaulter change if its center of mass rises about 4 meters during the jump. Okay, so once you write the question, let's draw a picture. Hopefully you know what a pole vaulter is. If not, you can look one up. So basically there is a vault that this pole vaulter has a pole, and he's going to run up and stick the pole in the ground right here, and he's going to fly over the vault. Okay, so he is doing work, converting his work to potential energy, so he has a certain amount of potential energy up here. He has a certain height above the ground. His height is 4 meters. Okay, we know that his mass is 64 kilograms. It's given in the problem. And we know gravity is 9.81 meters per second squared. So when we write our equation, potential energy gravitational equals mgh, we get 64 times 9.81 times 4. And we see that his potential energy is 2,511 joules. Okay, so not too difficult. Let's do one more. So this time we have a roller coaster. The roller coaster is starting at point A. It's a certain height above the ground. We only know its height in reference to point C. You'll notice that point A is above point C, 15 meters above, and then point B is 5 meters above point A. Okay, so let's solve for the first one. What is the change in potential energy from point A to point B? So we need to know it's changing from A to B. So our reference point, our 0, is going to be right here at A. This is our 0. So for letter A, we know that the mass is 1,000 kilograms. We know that gravity is 9.81. And we know the height in this case, it's rising 5 meters. So it's going from 0 meters to 5 meters. And when we solve for potential energy, you should get 1,000 times 9.81 times 5 meters. And you get 49,000 joules. Okay, for part B, what is the change from point B to point C? So now it's going from, our reference point is going to be this point at point B. So this is now going to be our height of 0. And now it's moving downwards. It's going down 20 meters. So we're going to have a negative height in this case. So potential energy for part B equals mgh. Same mass, 1,000 kilograms. Same gravity, always. And our height in this case is negative 20. So its energy is decreasing by 196,000 joules. So yes, it is possible to have a negative potential energy. If you are moving, if it depends on your reference point. Since our reference point is up here, that's our 0 point, we are going further below than where we started. So it has a negative potential energy.